Welcome to Engineering Dynamics. I'm your host, Dr. Walk, and today we're going to be talking about rigid body motion, specifically highlighting what pure rotation about a fixed axis looks like. So there are two examples that I think will help you visualize what pure rotation looks like. The first one is going to be looking at a propeller, and the blades of the propeller are all going to rotate at the same omega about the axis, and the axis would be the shaft that runs through the propellers, okay? And another one is going to be gears. Gears are a perfect representation of pure rotation about a fixed axis. Gears, so let me see if I have one here. Okay, so I have a few gears here. So let's look at a gear. This is a worm gear. You can tell that it's a worm gear if you flip it over. This worm gear has 4 teeth. Okay, so a gear is going to have a shaft that runs through it, and it's going to spin. Okay, so this spinning motion is going to, every point on the rigid body is going to spin about an axis. So gears inherently are going to be pure rotation. So if I'm looking at any point on my gear, I can relate that point to the center, and the center, it's going to act almost like an external pin. So it's not going to move, it's just going to allow it to rotate. Okay, so this great example. You can also have this type of gear. This is a herringbone gear, and when two gears mesh together, so we use gears, right, when we mesh them together. They can be meshed in two different types. They can mesh to create a simple gear train, or they can mesh to create a planetary gear train. Either way, when they mesh, we have what's called a no-slip condition. A no-slip condition means that when two gears rotate on each other, they're not going to slip. This is super important because when we get to the calculations, we can say that the point of contact will have the same velocity for this gear as it will for this gear, even if the gears are different shapes, or different diameters, like this gear is much bigger. Whatever that contact point is, because of the no slip condition, it will have the same linear velocity at that point. Okay, so for this one, if I drew my velocity vector, I would first draw the point of contact where they mesh. So like, this is hard to do backwards. So here, right here, and I would draw a line going straight down. That is super hard to do when I look into the camera. Anyway, maybe I'll draw it on the screen. So anyway, so the no slip condition, that's super important to understand because it tells us that the velocity vector at that point is the same. This is going to help us when we are trying to solve problems that involve gears. Okay, so remember no slip condition. We'll do an example at the end of the video where I kind of put that all together. So these are herringbone gears. And then what other gears do I have? Oh, this is a spiral bevel gear. So this kind of gear, you also use these types of gear in a rack and pinion. Do I have, oh, like this gear here. This is just a bevel gear. You can see the difference between the teeth. These teeth, they spiral, so they go at an angle, and these ones don't. So this would be kind of used in a rack and pinion type. Okay, so we saw, oh, this is another one. So these are our worm gears. Okay, so these are worm gears and they mesh together. These are 1, 2, 3, 4, 5, 6. These have 6 teeth. And when they mesh together, so you can kind of see, I can turn them and they mesh really nicely. Then when I turn this way, you can see that the shaft here and here, all of the parts on the green body, they're going to rotate about this center. It's so hard, this center. And then all of the parts on the white is going to rotate about this center. Okay. So when they mesh, when we compare points, say I have a point on the white body, I can relate that point to this center and it'll be in pure rotation. But then if I need to get over to the other side, I'm going to look at the point that they have in common. Okay, so that's the simple gear train. This is a simple gear train because they just mesh together. We also can arrange gears in a type that's called planetary gear train. A planetary gear train, this is kind of a simple example. You're going to have a sun gear, a planet gear, and a ring gear. You're going to have an input and an output. So here is one input option. When I, like say a motor would go here and it would have an input, what it's going to do is it's going to spin the sun gear, and the sun gear, which meshes with the planet gear, that will spin this, and this in turn will spin the sun gear. Okay, so here this is kind of the motion that we have. Okay, and then I could also use the sun gear as an input, and it would turn, here it goes, and that would turn this guy. Okay, so depending on what the input is. Anyway, that's the components to a planetary gear system. This is a simple example. They used this way back when, actually. It's called the south pointing chariot, and a south pointing chariot uses a planetary gear system, and they used to use it to travel way back in the day. So they would have their carriage and they would have their horses, line up, whatever, and pull them. Well, to decide where they were going in the right direction, they would point the chariot on the top to the south direction. And if the chariot moved a little bit, the guy stays still. So I'll represent this. I have it in my office. So here, I'll put it on the screen now. And what it does is basically you can travel kind of anywhere you want, but that south pointing chariot stays pointing in the same direction. So that's such an amazing part of planetary gears. Another thing we use them for is going to be in a car. So your transmission has planetary gears. If you want to look at the difference between a manual and an automatic and the efficiencies of why, they're different. So an automatic is going to be more efficient, and that's because you're not going to see lulls and like downward spikes in the efficiency graph. So like in a manual, I'm going to have to shift that back, and that shift moment is going to be a drop in power. If you use planetary gears and you use an automatic, the way that it's formed, you're never going to see that dip. So it's going to be more efficient. It's going to be more comfortable for your passengers. But again, that's kind of using that planetary gear system. I think I'll link another video if I can. It's somebody else's, it's not mine on YouTube, but they explain it really good. And they show all of the diagrams and stuff. So I'll link it here if YouTube lets me. Okay, so that is examples. I also have another example of a real world example using gears. So, your pencil sharpener. Don't laugh at me if you're super young watching this, okay? So back in the day, like you had this and you would put your pencil in it and you would sharpen it. Okay, if you take this cover off, you'll see that you have two gears that are meshing, right? So each gear is going to rotate about its own axes, and then the whole thing will rotate about the pencil, which is its own axis. So again, all pure rotation. Okay, so now that we've looked at some examples, why don't we go ahead and solve a problem and highlight that no slip condition. In real life, before we get started, in real life, how do we make sure that gears don't slip? What do we do? We put lots and lots of oil inside of our mechanism or fluid of some kind to make sure that they are meshing really nice and they don't grind or slip on each other. Okay, enough said. Example time. Okay, so here is our first example. We have two gears. Gear A, which is the smaller one, this is rotating gear B. And gear B, which has an extended drum that's attached to it. So this gear has kind of almost like a shelf that's attached to it, and that shelf is going to hold the rope as it turns up. Kind of think, if you're having a hard time visualizing this, kind of think of like a garden hose where you go like this to it and it like winds up, right, as you collect it. I hope I'm not confusing you more. Makes sense in my head. So anyway, it's going to be a little shelf and it'll sit on it, okay? So this middle part is called a drum, and the large gear is going to be gear B. Okay, so gear A, it is going to start from rest at t = 0 seconds, and its clockwise angular acceleration is given as a function of time by an equation alpha A equals 0.2 t radians per second squared. And my question wants to know, what is the linear velocity of my hook? Okay, my linear velocity of my hook. So my first question I usually make my students ask themselves, is this a kinematic problem or is this a kinetic problem? So I don't see any forces, so this is going to be a kinematic equation, a kinematic problem. So we are living in kinematics. And now I'm going to say, how many rigid bodies do I have at play? Here, I have 3 actually, right? So I know a lot of people want to jump to 2 because you have 2 gears, but really you have rigid body A, B, and H, okay? So when we look at rigid bodies, we can ask ourselves, what type of motion is each body undergoing? Okay, well, what type of motion is gear A undergoing? Pure rotation. What motion is gear B undergoing? Pure rotation. What type of motion is the rigid body H undergoing? Pure translation. Okay, so that's going to be translation. So what is our equations when we look at pure rotation? So you can write this in either a vector form or scalar. So in general, V equals, if we write it in vector form, omega cross R. Okay, if we write it in scalar form, it could be V R omega. Okay, so now let's look. So if I have another thing that we want to always locate on a rigid body is we're always comparing points, right? I can't say A is in pure rotation and just say that. I have to say all the points that are not on the axes are rotating about the fixed axis A. So I need to identify a point. Well, I want to identify a point that is common between rigid body A and rigid body B. I want a common point because I'm trying to compare the two to get information, right? To get that information, because I'm given information about gear A, but I need information about B, right? Which is then connected to H, okay? So kind of follow me here. So first I'm going to say, well, I have a point in the center and I can call that A. And then I have a point here, which is B. Now I want to identify what is a common point between A and B. Well, before we said that if we take 2 gears and we let them mesh together, that the point of contact, that is going to be the point that is in contact, right? So, and it's not going to slip. So here I am going to label another point. I'm going to label this point P. Okay, so now I have a rigid body AP and I have a rigid body PB. Ooh, those are not the best letters. Okay, we're going to try. And then I have another rigid body, okay, because I said H. I need to find a common point. The definition of a rigid body undergoing translation is that all of the points on that body will travel at the same rate. So that means that the point here will travel at the same rate as the point here. I hope you can see. So the point here will travel at the same point here, same point here, and same point here. So I would be inclined to say, to label another point here and call it H. Okay, so now I can say, okay, really I have a rigid body AP, PB, BH, and then just H. Okay, so let's work through this. Rigid body AB. I'm saying that P is in pure rotation about A. So again, this is going to be my rotation. I'm saying that P is also in pure rotation about B. So here we have again rotation. I'm going to say that H is in pure rotation about B, rotation. And I'm going to say that H is in translation. Okay, so now hopefully you understand the mechanism. Now let's go ahead and look at the equations. So we can first look at the gear A, and we know that P is in pure rotation of A. So I can say the velocity of P equals R omega A. I can also write this in vector form where it would be velocity of point P would equal omega A cross R P with respect to A. Either way is fine in this problem. If you need work with vectors, go ahead and do it in vector form, but it works both ways. So let's go ahead and work this out. So velocity of P equals, now R. R is the distance from point A to point P. So that's this distance right here. That distance is the radius of the gear, which is 50 millimeters. So this is going to be 50 millimeters times omega A. Omega A. Let's go back and look at what was given to us. We know that alpha A is in terms of time. And we were given at the beginning of the problem, which I forgot to give you guys, but we're trying to find the velocity of H at t equals 10 seconds. So at t equals 10 seconds, so we can take alpha A, let's do it over here. Alpha A equals 0.2t. To get omega A, I have to take its integral from 0 to 10 seconds, 0.2t. So this is going to be omega A equals 0.2t squared divided by 2. T is going to be 10 because I'm evaluating it from 0 to 10. So omega A is going to come out to be 10 squared times 0.2 divided by 2, which would be 10. Yes, 10. And that's going to be 10 radians per second. Okay, so that over here, I'm going to say that this is times 10 radians per second. So my VP is going to equal 500 millimeters per second. Okay, now my velocity at P, I don't have a direction here. However, because I didn't do it in vector form. If I did it in vector form, do you guys want to do it in vector form real quick? We probably should. Let's just do it one time so you guys see that it's the same thing, okay? So I'm going to take this equation, I'm just going to rewrite it right here. VP equals omega A cross RP with respect to A. VP, if I look at my, my point P and I look at it from relative to A, I see that's going around in a circle, and my velocity vector by definition is tangential to the curve and perpendicular to the position vector. So that means if this gear is rotating clockwise, because that's what it tells me in my directions, then my velocity vector is tangential to the curve and perpendicular to the position vector. So this is the velocity of point P relative to A. Okay, so this is going to be really VPJ equals omega A in the K direction cross 50 millimeters in the I direction. So now I have VPJ equals omega A we found to be 10 radians per second K. It is a vector, so you need to include the direction, cross 500 in the I direction. So VP is going to equal 500J. K cross J is positive, but this 10 is negative. So I put the negative there. So my VP is going to equal negative 500J. So if I do it my scalar way, I just have to know that, what direction it is, and you do. If you do it vector, it just confirms which direction it is. Okay, So now I know you guys can do it in both ways, vector and scalar. We can move on. So we have the velocity of p. Now we can do a relationship between the rigid body p and b. P is in Paul, B is in boy. So my rigid body formula, velocity of p equals omega cross r. This would be omega b cross r p with respect to b. Or I can write it as velocity of point P equals the angular acceleration of gear B times the distance between the point P and the point B. Okay, so velocity of P, we just found that. We can either use scalar form, which is going to be 500 equals omega B, and the distance between point P and B is going to be 200. So this radius here, which is given as 200 millimeters. So we're going to have 200 millimeters. So omega B is equal to 500 divided by 200. So 2.5. 2.5. And then I'm going to have radians per second, because this is millimeter per second. Millimeters cancel out, so I'm radius per second. Okay, now I did my equations for my first two rigid bodies, but now I need to say, okay, B is also related to H. How is that related? Well, we can say that if I'm looking at this point H, I can say that the velocity of H is in pure rotation, so I can write it as a vector, pure rotation about the point B. And the omega is of the gear B. Okay, now here is the sometimes a point of contention. The rate that the drum is spinning is the same rate as gear B because they are attached. So this omega B is the same as the one that we just found, okay? But the distance is not. The distance is going to be still the distance between point B and H. And that distance is the radius of the drum, which is 100. So we're going to say that the velocity of H is going to equal 2.5 times that distance, which is 100. And this is going to equal 250 millimeters per second, or 2.5 meters per second. Now, this one I didn't do a vector, but I know that the direction is up because of my diagram. That's why I can stay using scalars this whole time, because you can understand the mechanism and you know direction. A lot of times in dynamics, maybe it's not that simple and you're going to need to use vectors. So if you need to use the vectors, then you will need to go through each one, okay? Again, if you need practice, just go back and redo it. Anyway, that is my lecture on pure rotation for rigid bodies. We went over an example and we talked about different types of gears. I hope that helps, and I'll see you in my next video.